Good afternoon. Welcome to today's SCA webinar with Dr. Lee Richards on understanding well control fundamentals, making well control simple and understandable. Before we start today's webinar, we'd like to ask a few questions about the demographics of the audience. So I'm going to share some polling questions. And the first question is, what's your primary discipline? So we're starting to get some responses. We have some petroleum engineers in the audience, also some geoscientists. Still getting votes. Okay, most of you have voted at this point, so I'm going to close the poll for the first question and share the results. It looks like we have 70% geoscience and 30% petroleum engineers. So now I'm going to go to the next polling question. How many years of full-time experience do you have in the upstream gas industry? Starting some responses. Looks like we have quite a variety of experience levels. Most of you have voted, so I'm going to share the responses. 50% of you have 30 years experience, and I do have a representative sample in the other categories, except we don't have anyone with less than 1 year experience. So the next largest is 30% with 11 to 20 years experience. So thanks for sharing that information. Before I introduce Dr. Richards, I'd like to remind the audience that you are muted, but you can ask questions during the presentation using the GoToWebinar question feature. And Lee said he's okay if we interrupt him during the presentation, so be sure and just type your questions as you think about them. If you prefer to wait to the end, we'll cover the questions at the end as well. And you will be anonymous. So here's your chance to ask those dumb questions that you have that you've always wanted to ask. So let me make sure I'm sharing my screen. And I'm going to do a few introductory comments. This is Understanding Well Control Fundamentals, Making Well Control Simple and Understandable. And we'd like to welcome today our instructor, Dr. Lee Richards. Lee is a PhD and a professional engineer. He is an accomplished engineer who's worked for both Halliburton and BP America. He's currently assistant professor of petroleum engineering at Montana Tech, and he also consults for clients around the world. He's co-authored a number of presentations and publications, and he received his BS from Washington State and a PhD in chemical engineering from Montana State. So for SCA, Dr. Richards teaches 3 classes: drilling fluids, introduction to drilling engineering, and well control for drilling engineers and senior rig personnel. That last course is the one we'll be talking about mainly today, and it's being offered in Houston, Texas in August 15th through 18th in person. The other 2 courses are being offered in Midland in June. So Introduction to Drilling Engineers is June 6th and 7th in Midland, and Drilling Fluids is June 8th through 10th in Midland. So you can take both of those classes during the same week in Midland. We'd also like to make note of some of our online classes that are being offered in live online format virtually. These are generally done in half days. And so you can see we have several courses that are coming up in live online format. The CCUS class in the engineering perspective is just around the corner, starting May 17th. We also have Principles and Practices of Mud Motors, June 6th, and Refrac Candidate Selection also starting on June 6th. So there's some virtual opportunities for those of you who are in different parts of the world and prefer not to attend in person. We can also bring training courses to your location, so make sure you contact us if you see a course advertised and you would like to have it taught in-house. We can certainly make arrangements to do that as well. Also look to SCA for all of your consulting needs. We do projects and studies in addition to training, and we also provide direct hire services both for contract and full-time hires. So I'm going to pass the presentation rights over to Dr. Richards and let you take it away. It's all yours.
Okay. Susan, can you see my understanding well control fundamentals?
I can.
Okay, just making sure we're on the right screen. Welcome everybody. Thanks Susan for that introduction. As Susan mentioned, I am a college professor and I consult on the side when need be, when people need my services. Thanks for coming to this presentation. It may be a little different than what you're used to. So as a professor, you know, I look very carefully at how people learn, and the general PowerPoint presentation that people just go through, we just flip up slides and we talk about the slides. It turns out that very little retention comes from that. So we're trying something new this year with these with our courses. They'll be interactive. I have slides, but I will annotate the slides as we go. I'll apologize ahead of time. My handwriting may not be the best, but I think that this interactive format is a much better way to get the information across and keep our audience engaged. So with that, we'll get going. So this is understanding well control fundamentals. This presentation, it may be a little bit basic for some of you, and others of you it may not. But again, my teaching philosophy for all of these things comes from being in the field my whole career, and I felt that most well-controlled courses did not actually teach people the fundamentals of what was going on. It was more use this formula in this situation, and or teaching towards just passing a test. And I don't believe that that is fundamentally helpful for engineers to understand what's going on. So part of this is going to be pretty basic, and we'll go through it relatively fast, and we'll get to maybe a little bit more advanced topic towards the end. But the overall goal here for all of my classes is one, to make them pretty laid back and interactive. So with that, I want you to ask questions when you can. I'm happy for you to interrupt me at any time, ask a question anytime. I can answer the questions as they come along, or I'll answer questions at the end. The other goals for my classes are that people actually learn and don't just sort of zone out and die from death by PowerPoint. So making well control simple and understandable is the goal, and we'll continue on here. Today, what I'm going to be talking about is we'll start with understanding pressure, and this is very basic, but it's super important. It's important for well control, but it's also just important to understand how pressure works as a safety aspect when working around it, but working on a rig especially. We're going to talk about hydrostatic pressure. Then we'll talk about formation pressure. We'll talk about what happens while we're taking a kick and what the pressures look like while we're taking a kick and how they form in our wellbore. We'll talk about how the wellbore becomes a U-tube, and you'll see what I mean by that going forward. Then we'll determine bottom hole pressure, and from that we'll actually be able to determine kick density to a relatively high level of precision, good enough to know what you're dealing with. Going forward, so we need to be able to understand our pressure sources before we're going to be able to understand how they interact with our wellbore and how we respond to those pressures. And they're actually very simple. It really comes down to just hydrostatic pressure and formation pressure. Okay, and most of the time that's all we're going to have to deal with in these situations, if our wellbore is static especially. But this is a topic that we'll talk about in the whole class, or if we took the entire class. But the added pressures, which aren't applicable most of the times, but things like pumps and pipe movement. Is there a question? Okay. Somebody's not muted.
No questions.
Yeah. Okay. So the pump pressures and pipe movements certainly add to the situation, and we would cover that going forward. But for today, we're just going to look at static pressures. And again, it just comes down to hydrostatic pressure and formation pressure, and it ends up being really simple if we treat it properly. So first off, just understanding pressure as a whole. And it's easiest to do this by just thinking about the units that we talk about in the US oil field. And we talk about PSI, which is pound force per inch squared. So that's basically 1 pound of force acting on 1 inch squared. So I've got some examples going forward. It's relatively easy to get your head around when I show you these. So one example I like to talk about is a Bayrite tank. And I did a quick calculation. So if you think about an upright Bayrite tank that you hold bulk Bayrite in for mud product. So if we have a Bayrite tank, and we usually pressure those up to 10 PSI. 10 pounds force per inch squared, okay? And we think of 10 PSI, that's nothing, right? Like that's not dangerous. It's nothing to really worry about too much, right? We think about high pressures that we have in our well bores, like, you know, we may be running 4,500 PSI standpipe pressure, or maybe if we have a 7,500 PSI rig, we're running 6,800 PSI standpipe pressure, something like that. And we think, man, those are really dangerous pressures. But the thing about pressure is it is force per surface area. So if I have a Bayrite tank, and I did a quick calculation, and the surface area of that Bayrite tank is roughly 110,000 inches squared. So if we take 10 pounds force per inch squared and we multiply that over 110,000 inches squared, okay, we end up with 1.1 million pounds force. So it actually ends up being an astronomical amount of force contained in this Bayrite tank, even if it's only 10 PSI, because the surface area is so large. So that's just one example I like. That's sort of a safety thing, that low pressures in over a high surface area is a great deal of force. And understanding that concept going forward here is, I have an example of a normal, like a 200-pound man. And if he's standing on an 8-inch by 12-inch square, and his weight is distributed evenly on that square, the surface area of that square is 12 inches times 8 inches, and I get 96 inches squared. Okay, so if I have 200 pounds force, and I divide that by 96 inches squared, that gives us our units of pounds per inch squared. I end up with something like 2.08 inches, or sorry, pounds force per inch squared. Okay, so 2.08 or 2.1 PSI, no big deal. But if I have that same guy and he's standing on something that looks like this triangle I have here, and all of that weight is then centered on 1 inch squared, let's say he's got really good balance. And if this is 1 inch by 1 inch, I go 1 times 1, that equals 1 inch squared. It's pretty obvious. And if I have 200 pounds force per 1 inch squared, I end up with 200 PSI. Okay, so the same amount of weight acting on a smaller surface area gives me a much higher pressure, and the same amount of weight acting over a bigger surface area gives me a lower pressure. And I know this is very obvious to some of you, and some of you have your brain around this perfectly, but a lot of times we're not thinking about these things that are just under our nose. And it's important to understand this fundamental concept going forward when we start talking about fluid pressures in a wellbore. So a couple more examples here of this, just so we're sure that we're all on the same page. So if I have a column of fluid, and let's say that column, just to keep, and we're looking at it and it's just a square column of fluid like I have here in the picture. And just to keep it simple, if it's 1 inch by 1 inch on each side, and that column of fluid weighs 400 pounds, and I have 1 inch by 1 inch, that equals 1 inch squared, I end up with 400 psi, 400 pounds force per 1 inch squared, 400 psi. Okay, still pretty basic. Okay, and now I have the same height column, but now it's a larger volume, let's say. And let's say it is 2 inches by 2 inches, 1,600 pounds. So now I have 2 inches by 2 inches, and I have 2 inch times 2 inch equals 4 inches squared. And if this column of fluid is the same height, and that meaning that, and it's the same density, which it will be in this case, it is going to be the same pressure. So if I had 1,600 pounds force per 4 inches squared, I end up with 400 psi, just like I did in the previous example. Okay, so this is the point of this is that the pressure exerted by the fluid does not depend on the volume of fluid. It depends on the height of the fluid and the density of the fluid. So going back, showing that again, if I had a fluid column, it's the same as example 1, but it was 2 times taller, let's say. Let's say this was 2 times example 1. In example 1, the weight of the fluid was 400 pounds. And I multiply that, since it's twice as high, now it's the same density fluid, but now it's 800 pounds of fluid. And that is acting over 1 inch squared. Okay, now I'm going to have 800 pounds force per 1 inch squared, and I get 800 psi. Okay, and this, we could alter the density. You could make it the same height, make it twice as dense, and it would be the same amount of pressure. You could make it twice as tall and half as dense, and you get the idea. So it's really important to understand this concept when we go forward with looking at hydrostatic pressures in a wellbore. Sometimes I feel in the oil field, we forget what's really going on in the system because we use formulas that have been given to us from the very beginning, and we don't necessarily know where those come from. One example is the hydrostatic pressure equation. In the basis of it all, it's very simple, but we're so used to just using hydrostatic pressure, which I call here as P-Hyd, and it's quite frequently called other things, but I'm just going to call it P-Hyd for this presentation. I think it's very simple, and we don't get things mixed up with other things doing that. So P-Hyd is equal to 0.052 times the mud weight in pounds per gallon times our TVD in feet. And we've seen this, we've used this 1,000 times, but quite frequently when it's put forward to us in a well control class, we don't talk about where it comes from. And what this comes from is just simply that P-Hyd is equal to the density of a fluid times gravity times the height, and this being density, this being gravity, acceleration of gravity, and this being our TVD, in which case this is the vertical height. Okay, and this is what that formula comes from. The 0.052 is just simply a correction factor that includes gravity and unit conversions to go from pounds per gallon times feet and into pounds force per inch squared. As you can imagine, there's quite a few unit conversions going on in there. So it's actually a really simple formula that we use quite a lot. So let's look at this as we use it in a wellbore. So let's say we have a wellbore here, and this brown is drilling fluid. Okay, and let's just say we've got 10 pounds per gallon drilling fluid. And that is, let's say we've got a shoe set at 10,000 feet TVD. Of course, if it was, say, 20,000 foot measure depth, it wouldn't matter. It's only the vertical height of the column that matters. It doesn't matter how wide the column is. It doesn't matter what area the column's spread out over. It matters the density and the actual vertical height. And let's say the TD of the well is 12,000 feet TVD. Not to scale, obviously. So this is pretty simple. We've probably all done this, but we just have to be clear that we know how. The p-hide at the shoe would be equal to 0.052 times the mud weight, 10.0, times the vertical depth, 10,000 feet, and that ends up being 5,200 psi. Okay, so we would have 5,200 psi pushing down in that case. Now, on a side note, and this becomes really important, it's a little off topic here, but it becomes really important in well control to understand that I just said we had 5,200 psi pushing down at this point. Well, the reality of it is that pressure is pointing in all directions. It's pointing up, it's pointing down, it's pointing sideways. It's an important concept to understand when we talk about opposing pressures. So just another quick example. I'm a big fan of examples because I think it's important for us to see how things work. If we look at the hydrostatic at the TD, that's just the same thing, 0.052 times 10.0 times 12,000. And I end up getting 6240 psi. Just a couple of different examples. So we would have right here 6240 psi at the bottom of the wellbore. Okay, so all pretty simple. We've probably done these things before, but again, important to understand where hydrostatic pressure comes from. So now let's look at what happens when we take a kick. Okay, when we take a kick, basically the kick conditions, and let me annotate that here, kick conditions are usually are when the formation pressure, and I'm calling formation pressure P form, okay, when P form is greater than the bottom hole pressure or the hydrostatic pressure in my mud. Okay, and if the well is static, and let's just think about the well being static right now, it is simply hydrostatic pressure. If the well is not static, it is when P form is greater than the hydrostatic pressure plus the pressure loss due to friction in your annulus. And generally we think of these things as an ECD when the wellbore is not static. Okay, so basically, I mean, it's real simple. That when formation pressure gets higher than bottom hole pressure, we take a kick. And that's nearly without exception. So the formation pressure, once we take a kick now, we are going to, when we look at this in a well control situation, while we're taking a kick, that formation pressure is higher than our bottom hole pressure. Soon as the bottom hole pressure gets to the point of where it equals formation pressure, the well stops kicking. How does that happen? Well, if your well bore is open and you haven't shut it in, the only way you're going to bring that pressure up to keep the well bore from kicking, keep the formation from kicking, is to either raise your mud weight, increase the density, or to shut in, well, if you haven't shut in, to pump harder so that your ECDs go up, okay? But if you do have a shut-in well bore, what ends up happening is soon as you shut your BOPs here, if you shut these BOPs, okay, then the well bore becomes a pressure vessel and it's sealed. And the formation will kick until the hydrostatic pressure plus the trapped pressure, then trapped pressures you're going to see as shut in drill pipe pressure and shut in casing pressure. Okay, and these will be different for reasons I'll talk about going forward. But soon as that trapped pressure plus the hydrostatic pressure in your well bore equals the formation pressure, that is when the well bore stops kicking. Okay, and then the well bore will be static at that point. It will no longer be taking an influx. Okay, so at this point, we can actually determine formation pressure, and that's what we're going to look at going forward. So to make this simple, let's just look at a well bore that doesn't have drill pipe in it, just to make it nice and simple. And let's look at this in a scenario where we've taken a kick, okay, and we've got surface. I'm just going to call this piece surface right here, okay. We've shut in our well bore, our BOPs are closed, and we've got some sort of surface pressure. And realistically, this would be casing pressure, but there's no pipe in the hole for this example. So we have hydrostatic pressure of our drilling mud, which is brown in this picture, and the kick that is red here. So we have P hyd of mud that is pushing down at that point to that depth, wherever the top of the kick is. Excuse me. In addition, and we forget this, and we don't think about this quite frequently, but we have the hydrostatic pressure of the kick itself, okay? That kick fluid in there, and that has a column, a pressure column associated with it. And here we've got our formation pressure pushing in, and at this point when we when we start taking a kick, the formation pressure is higher than the hydrostatic pressure of the mud, so we start taking a kick. The kick comes in until the surface pressure plus the hydrostatic pressure in the well bore are equal to the formation pressure. So let's look at this right here. The hydrostatic pressure in the well bore and that, again, I'm going to call that P hyd. In this case, just the hydrostatic pressure is equal to P hyd of the mud plus P hyd of the kick. Okay, two columns of fluid, okay? So the bottom hole pressure in this case, bottom hole pressure, once the kick has come to equilibrium, at equilibrium, okay, the bottom hole pressure is equal to the hydrostatic pressure, the total hydrostatic pressure, okay, plus the surface pressure. Again, the pressures we have here are the hydrostatic pressure of this column of fluid, okay, the hydrostatic pressure of this column of fluid, of the kick fluid, okay, and then I'll rewrite P form here to make it look more like it's at the bottom of the well bore, and I'll put it in a different color. I've got P form. Okay, so I've got these two hydrostatic pressures, the formation pressure, and then, so if I add these two up, I take P hyd of the mud, P hyd of the kick, and P surf. So what I end up with is P hide of the mud plus P hide of the kick plus the surface pressure, which in this case is shut-in casing pressure, is equal to the pressure of the formation. Okay, so with this, we can use this to calculate formation pressure after we've taken a kick. And once we've calculated formation pressure, we can calculate a kill weight mud and figure out how to kill the well. Okay, so let's make this a little bit more realistic here, and let's look at the actual situation that we have. If we add drill pipe to the system here, we have the annulus on the outside that has both kick fluid and drilling fluid in it. And then we have our drill pipe on the inside that has just drilling fluid on it. Because when you take a kick, you are not going to take a kick up the inside of your drill pipe most of the time. There's two reasons for that. One is you've got a float in the system. Now, I'll give it, and that float is a one-way valve located in right on the top of your mud motor, which in this picture right here would be right about there. Okay, and if you have a float in the system, that is supposed to keep things from going up your drill pipe. Well, anybody that's been around them knows that they leak most of the time, so that actually may not be doing it. But the simple matter is that you're usually drilling, so you're pumping fluid down the inside of your drill pipe. And when you take this kick, since you're pumping fluid down the inside of the drill pipe, there's no opportunity for the kick to go up your drill pipe since you're pumping. Then when you shut your pumps off, you have a relatively incompressible fluid inside your drill pipe. And when you shut the pumps off, barring the pumps running backwards, fluid cannot come up inside that drill pipe because there's a set volume of fluid that's already there, right? So what ends up happening is you end up with a pure column of drilling mud inside your drill pipe. Okay, so to understand this system, we need to look at this as one big pressure vessel, and we do that by looking at it as a U-tube. So what that looks like here is basically I'm going to take this Wellbore and I'm going to split it into two pieces. And this is just an easier way of looking at it with my annulus over here on the left and my drill pipe, the inside of my drill pipe over here on the right. Okay, so if I do this, and I will have, if this is shut in, let me shut my BOPs here, okay? If this is shut in, I'm going to end up with my shut-in casing pressure here and my shut-in drill pipe pressure over here on that gauge. And it much the same, the analog is here. I would have a gauge that shows my shut-in casing pressure, and I would have another gauge here that shows my shut-in drill pipe pressure. Okay, and we can look at this. This is just a really convenient way to look at the situation, and then I can split it in two sides. I have a pure column of fluid, of drilling fluid, on the right on my drill pipe side. Okay, the bottom hole pressure, BHP of my annulus. Okay, if I have that, that equals, if I'm shut in and it's come to equilibrium, it equals P formation. Okay, and the bottom hole pressure on my drill pipe side also equals P formation because they're equal. Okay, both of these are equal here. Okay, they're going, unless, so I have this column of fluid on the right and the column of fluid on the left. The hydrostatic pressure of the column and the fluid on the left plus the shut-in casing pressure is equal to the hydrostatic pressure of the column of fluid on the right plus the shut-in drill pipe pressure. And we'll look at that a little closer here going forward. Okay, so let's look at just the shut-in drill pipe pressure, okay? So our bottom hole pressure, if we're just looking at the right side, would be equal to the hydrostatic pressure in my drill pipe, and I'll put DP, okay, plus my shut-in drill pipe pressure. Because this column of fluid, again, on the right is a pure column of mud. So it is pretty easy from this to find our formation pressure, because at this point, like I said before, our bottom hole pressure is equal to our formation pressure. Okay, so with this, we can use this to find the kill weight mud, because now we have P form is equal to P hide on my drill pipe side plus my shut-in drill pipe pressure. Okay, and the shut-in drill pipe pressure is known. And this is known because we knew what mud weight we were drilling with. At least we should. This is why we need to be taking a mud weight all the time. And we can use this to find the kill weight mud. Okay, so just a quick example calculating kill weight mud here. So if the mud in the drill pipe is all one density, let's make a quick example. And let's say we have a 10,000 foot TVD well. Okay, and I'll use my standard 10.0 ppg drilling fluid. Okay, just to make this easy, if my shut-in drill pipe pressure is 500 psi, okay, so then my hydrostatic pressure is equal to 0.052 times 10.0 times 10,000 feet, and that equals 5,200 psi. Done that before. Okay, and then so my formation pressure is equal to 5,200 psi plus 500 psi. My shut-in drill pipe pressure, that equals 5,700 psi. And from that, I can calculate my kill weight mud by just manipulating the same equation. So I know 5,700 psi is equal to 0.052 times, now I'm going to just substitute in equivalent mud weight, which I actually could put kill weight mud in this case, okay, times the depth. I'm just converting this 5,700 psi into a mud weight now, and when I do that, I get 5,700 divided by 0.052 times 10,000, and I end up with 10.96 pounds per gallon, and I would round that up to 11.0 pounds per gallon, and that would be my kill weight mud. Okay, I'm going pretty fast through this, but it's pretty simple. This is just being able to look at a pure column of fluid on the right and determining what that kill weight mud is going to be, because we know exactly what the formation pressure is there. Okay, so now we can, so we already did that, calculated kill weight mud. We don't need to go over that again. Now, if we look at the shut-in casing pressure, it is going to be different. These two are not going to be equal. And the reason they're not equal is because the hydrostatic pressure resultant from the kick fluid is different than on the right side. There's a pure column of fluid on the right side. There is a column of kick fluid on the left side, or in our annulus. That kick fluid is lighter than our drilling fluid, in almost any case it's going to be. And the heaviest it could be is if we took a saltwater kick, and it might be something like, I mean, I guess it could be like 10 pounds per gallon. Generally, you're not going to take a kick with a fluid that's heavier than your drilling fluid. So from this, we can also figure out a few things about our wellbore. So we have right here, the pressures on this side are equal to the hydrostatic of our mud, and this is on our annulus side now, plus P hyd of our kick, okay, plus the shut-in casing pressure, and that is going to equal P formation. Okay, and we knew this, we learned that from our shut-in drill pipe pressure. Okay, do we know these is the question. We know this is known. And I will actually say, we know the hydrostatic pressure of our mud because we know the density of the mud, and we should actually know the height of the mud if we know the volume of the kick, okay? And we should know the volume of the kick by the amount of extra mud we have in our pits. So if we were drilling along and we had 1,000 barrels of mud in our pits, when we took a kick, now we have 1,050 barrels of mud. Where did the mud come from? It's because we took a 50-barrel kick that displaced 50 barrels of mud into our pits. So we know the volume of the kick. If we know the volume of the kick, we know our annular clearances, and we can determine the height of the kick. And if we know the height of the kick, we can calculate the height of the drilling fluid, and from all of that, we will be able to back calculate the density of the kick. So we need to know this kick size, and the kick size is really important to be able to tell the densities. And once we calculate the density, we'll be able to tell what type of kick we took, and this is really important in a well-controlled situation. So if we think about 2 pounds per gallon being pure dry gas, or 2.2 pounds per gallon, roughly 7 pounds per gallon being crude oil, and 8.6 to 9.8 being brine, if we determine the approximate weight of our kick fluid, or approximate density, then we can determine what the kick fluid is. So as I said before, we know our bottom hole pressure, and we learned that from the shut-in drill pipes pressure, and we know the kick size because we are monitoring our pit volumes, something I talk about to a great deal in my class. It's so important to know how to monitor pit volumes accurately, and we don't do that very well in the oil field, at least on US land. So we can calculate the height of the kick from that volume, and the height of the kick is known, but the density is not, so we can solve for it from our shut-in casing pressure. So what that starts to look like, if kick size is known, then kick height can be determined using the annular capacity. So then let's see here. Let's do a quick example. I think I have time in the next couple of minutes. So let's do an example. So if I took a 10-barrel kick, okay, and I was drilling with my 10 ppg mud weight, okay, and my bit depth, is my normal 10,000 feet, making it nice and simple. And we'll say that that's a completely vertical well. It's TVD and MD, okay? And let's say I had a shut-in casing pressure of 500 PSI, shut-in drill pipe pressure of 400 PSI, okay? So, and let's say my annular capacity around my drill collars was 0.05 barrels per foot. And of course, I would determine that by the geometry around my drill collars. Okay, so for this example, to keep it nice and simple, so if I knew I had a 10-barrel kick, and I knew that 1 foot of my annulus, 1 foot per 0.05 barrels, and if I did that calculation, if I divided my 10 barrels by 0.05, I would end up with 200 feet. These units would cancel out, and I would end up with a 200-foot height. So this is going to be 200 feet. Okay, and that would be MD, but since this is a vertical well, it is also TVD. And so the TVD of the mud would equal 10,000 feet minus 200 feet, because this was 10,000 feet, the whole thing. So this here ends up being 9,800 feet. Okay, so then the hydrostatic of the mud would equal 0.052 times 10.0 times 9,800 feet, and I end up getting 5,096 psi. Okay, and the hydrostatic pressure of the kick is unknown. Okay, and I think I'm going to run out of space here. I'll try to make it nice and small and not super cluttered. I'm missing an extra slide I put in here. So from our shut-in drill pipe pressure, that being 400 psi, I know on this side, I'll do this calculation here. I know my hydrostatic pressure on this side is 5,200 psi. And if this shut-in drill pipe pressure is 400 psi, P form is equal to 5,200 plus 400 equals 5,600 psi. Okay, all right. So if I have 5,600 psi, oh, let me make this. I actually made a mistake here in my example. This was supposed to be 480 psi, just to make it a little simpler for calculation's sake. So I know this is my formation pressure, and I know that I've got this hydrostatic pressure of the mud on my annulus side. Okay, so now I can determine the hydrostatic pressure of the kick, because I know that the pressures are equal on both sides, the total pressures. So I know on my annulus side, I've got 5,600 psi is equal to 5,096. This is the hydrostatic pressure of my mud on my annulus side. Okay, this is all annulus side now, plus P hyd of my kick, plus my shut-in casing pressure at 480 psi. So if I do that math, I determine that my hydrostatic pressure of my kick, let me just do this to make sure I didn't make a mistake. I end up with the hydrostatic pressure of my kick equals 24 psi. Okay, and if I know that the kick is equal to 200 feet high, I have equals 0.052 times the density of the kick, and I'm going to call that equivalent mud weight here, EMW, times 200 feet. And if I solve for all that, I end up with, and I apologize, I'm running out of space here, 2.2 pounds per gallon. Okay, and if it is 2.2 pounds per gallon, I know that it's probably pure gas. So all of that stuff that they cover in a well control class, but again, I don't think they go into the fundamentals of why it is what it is. So in conclusion, it's just a pretty simple introduction to pressures and how they can be simplified into just hydrostatic pressure, formation pressure, and surface pressures in a static kick situations. All these pressures are going to come into equilibrium eventually, and it will stop kicking. We will be able to read surface pressures. Bottom hole pressure we can determine using our shut-in drill pipe, and then we can get kick density from our shut-in casing pressure, and from that we will know what type of kick we took. So with that, I will open it up to questions. I know that was a pretty basic introduction to a couple of principles, but I think they're really important. So if anybody has any questions, I'd be very glad to answer them.
Thank you. I want to remind everybody you can post your questions in the question feature in your GoToWebinar dashboard. Later today, you will receive a link to a recording of today's webinar, an evaluation form, and a link to register for well control for drilling engineers and senior rig personnel. That's scheduled for August 15th through 18th in Houston, Texas. The first question, there was an acronym that you used, ECD. What is ECD?
I'm going to go ahead and annotate. ECD stands for equivalent circulating density. I should have thought ahead and put in a blank page here, but I will just, ECD is equal to equivalent circulating density. And basically, if we have our hydrostatic pressure, and that hydrostatic pressure of say 10-pound mud weight in a 10,000 foot well bore, as we saw in the presentation, is 5,200 psi. Now, if there is an additional 800 psi of pressure loss above the bit in the annulus, that pressure, the well bore's seen that pressure too. So if I had my hydrostatic pressure equals 5,200 psi, and delta P friction, this would be our pressure loss due to pumping. Basically, there's friction losses to move the mud, and we talk about this for quite a bit in the course. Let's say that's 800 psi. The total pressure is equal to 5,200 psi plus 800 psi, and that would be 6,000 psi. This would be the pressure the formation is seeing, and if we convert that into an equivalent mud weight, we call it an ECD. And to do that, again, and I apologize, I don't have a blank page here, I would have 6,000 is equal to 0.052 times my ECD times TVD. And I would just do, let me move that over. 6,000 equals 0.052 times ECD times TVD. I would know TVD, and I would just solve for ECD in that, and I would have my equivalent circulating density.
Great. Next question, how do you determine the volume of the kick?
The volume of the kick is basically just from pit gain. Again, if we're drilling along and we've got 1,000 barrels in our pits, we take a kick, we shut in, and we look, and now we've got 1,050 barrels. We took a 50 barrel kick. Now, it gets more complicated than that, because if you've been on a rig at all, you know that our pit monitoring systems are frequently less than perfect. So what we end up needing to do is something called fingerprinting our well. And I talk about that in the course for it. It's a actually relatively involved process. It's very simple, but basically what we have to do is look at what happens every time we turn off our pumps and see what happens to our wellbore volumes as they equilibrate when the pumps are off. So again, it's basically pit gains. Now, if you are on an managed pressure drilling situation, you should be able to determine the volume of the kick exactly just from flow in minus flow out, where they're monitoring the returns with a Coriolis flow meter. Then we can be done exactly. But on a normal drilling operation, like most of us encounter on US land again, we just look at how much is left in the pits, and there's a few tricks to that.
Next question, how frequently do kicks occur?
Hopefully never. That's all of our goal. So that's another part of the class. I mean, we talk about handling the kick. Of course, that's a big part of a well control class, is what do we do when we take a kick? But really the most important part of the well control class is what do we do to avoid a kick? And to answer that question again, it hopefully never. Hopefully you've done all the right things to just avoid a kick. Excuse me, but they you could be in an area where you don't know what's coming, a lot of unknowns, and they could happen more frequently, but generally they shouldn't happen very often. But when they do, you need to know how to handle them.
How are the calculations made with underbalanced drilling?
Okay. Depending on the question, I guess depending on what the question is asking, I could go a couple of ways. Excuse me. I got a little throat here. I think they're probably talking about managed pressure drilling, in which case we're basically going to look at the formation pressure, and we're going to look at our hydrostatic pressure, and we'll be able to see how much underbalanced we are as the difference between the two. So if I said delta P underbalanced, I just call that UB, I guess, right, for now. That would equal to P formation minus the hydrostatic pressure. And this would be under static conditions. If I wanted to, if I was underbalanced during dynamic conditions, it would be minus my delta P, change in pressure due to friction, in my wellbore or my pumping losses as well. So I think that answers that question. But again, I could go into that in great detail in a lot of different aspects given more time.
When do you use managed pressure drilling?
That's a great question. When you use managed pressure drilling is when you can't get away with regular drilling. So if you have really tight windows, meaning your ECDs are approaching your shoe fracture pressure or injection pressure, whatever you want to call it. We generally call it fracture pressure or leak off test pressure. If those ECDs are starting getting really tight to that, then MPD becomes an option. If you cannot control losses without taking a kick because you're in such tight margins, that's when MPD becomes very important. Furthermore, it comes down to risk tolerance in that you're going to be spending more money for the MPD system, but if your risk tolerance for that given well or that given interval is not high enough to operate without the system, then you need it. So again, that was a short answer to a long question.
How can you control losses?
Well, there's lots of ways, but generally we're going to control losses by lowering our mud weight. And therein lies the problem with ECDs and managed pressure drilling, that if we lower our mud weight, we get closer to taking a kick. So managed pressure drilling allows us to control losses when our ECDs need to be higher in order to take a kick.
How do you make sure that you're not weighting up so much that you cause formation damage?
Okay, we should know that from our leak off test and formation integrity test. So if we have a leak off test of say 16 pounds per gallon, and we know our ECDs are currently at 15 pounds per gallon, we better not weight our mud up to anything past where our ECDs would be getting close to that 16 pounds per gallon.
Excellent. Well, I think we're at the top of the hour, so I'd like to thank our audience for attending today's webinar. Later today, you'll receive a link to the recording of today's webinar and evaluation form, and a link to register for well control for drilling engineers and senior rig personnel scheduled for August 15th through 18th in Houston, Texas. Thanks for attending. Goodbye.
Thank you.